Let us examine the capabilities of Ocular by analyzing Hello ShiftLeft. Hello ShiftLeft is a simple open source Java-based microservice application with seeded vulnerabilities simulating financial service function. Let us pay attention to one specific implementation in Hello ShiftLeft that caters to serving RSS feeds. The backend engineer has designed this REST API endpoint to dynamically load any feed given its name. For example, if alert as a category is requested, then alert.rss is looked up in the file system and appropriately returned in response to the request. Let us examine the inner workings of this function. This function, getRSS for category unsafe, responds to any request initiated on the route /RSS unsafe /category. Note that the category is passed as an input parameter to this function. As a request is initiated with an appropriate category name, a file path is created by appending the category name to the restricted directory configured. After the file path is created, it is passed to the constructor of the file input stream, where the input stream is initialized, raw bytes are read from the file system, and a response is crafted. What could go wrong in this flow? Let us examine a typical request initiated upon this flow. If a user tries www.hello ShiftLeft.svc with the category name financial reform, the appropriate RSS file is looked up in the restricted directory and loaded in response. Now, if an adversarial entity or a hacker attempts to interact with this route, but rather than passing a category name, he passes an escaped path to the etc host file, guess what? The system responds with a host file from etc host. Compromised, isn't it? Many file operations are intended to take place within a restricted directory. By using special elements like ... or / separators, attackers can escape outside of this restricted location to access files or directories that are elsewhere on the system. So this particular function is vulnerable to a path traversal attack. Now let us process this function using Ocular. First, we clone the project Hello ShiftLeft and package the Hello ShiftLeft in order to create a executable artifact. Given that this is a Java application, a jar file is created as a consequence of building this package. The next course of action is to create the semantic code property graph by passing the jar file as an input and creating a graph representation of this archive as an output. This process takes less than 15 seconds. And after the graph is created, we are going to load that graph in Ocular's interactive console. The graph is loaded by using an API load CPG. Now the graph for Hello ShiftLeft has been loaded into the namespace of Ocular's interactive console. The various Fluent APIs that can be executed within this console to conduct enquiries on Hello ShiftLeft. So in this case, I'm looking up all the methods with the absolute name, which is essentially the package name, prefixed to the class name, to the method name in Hello ShiftLeft. Likewise, I can look up all the dependencies that Hello ShiftLeft depends on from an open source perspective. Now let us go ahead and identify all sources of interaction in Hello ShiftLeft. Sources of interaction are all controllers hosted in Hello ShiftLeft. In this case, there are several controllers that have been implemented to represent different financial functions. So what I've just executed are all method names with prefix controller and those that accept a string as an input. I've taken the results of this particular Fluent API and assigned it to source. The next action is to look up all implementations or utility of file input stream in any method in Hello ShiftLeft. Now, the output of this particular Fluent API has been assigned to sync. So the next query that I'm going to execute is to conduct reachability. Reachability from source to sync, meaning any place where file input stream is utilized that accepts an input parameter that has been passed from an API request without validation. Now, based on the results that I've received, I'm going to print the flow trace. The flow trace is a pretty printed representation of the entire flow that emerges from the source and reaches the sink without validation. So in this case, I emphasize on validation because in Hello ShiftLeft, there is an implementation of path validation in the common folder that has a method called as validate RSS feed. This method essentially replaces any escaping in the category name that was applied with an malicious intent. So this flow sequence is essentially a representation of a particular method that does not conduct validation of untrusted input, which could essentially lead to a path traversal attack. Now let us go ahead and actually again use a Fluent API to extract a potential recommendation associated with this vulnerability. Now this recommendation contains the flow trace that holds the parameter, the line number, the method name, and the file name from the point of trigger of the API to the point where it interacts with the file input stream without validation. The recommendation also contains remediation proposals, meaning conduct appropriate input validation at the API endpoint or use a reference map in order to check if any RSS feed requested is not escaping the restricted directory. Now, if an auditor is interacting with this console, it would be appropriate for him to take this recommendation and feed it back into the GitHub project so that an engineer can act to remediate this incident or issue. Again, using Fluent API, I initialize the GitHub token so I can interact with GitHub and essentially seamlessly integrate with the workflow of the engineer. Using Fluent API, I create an issue in GitHub. Now let me revert back to the project and click on issues. Now the appropriate description of the issue has been logged in with enough data to drive remediation. So with this, I have demonstrated that Ocular has the capability of conducting deep semantic analysis and thereafter seamlessly integrate with the workflow of engineers. Thank you.